Hi guys. So this is just going to be a quick video of me explaining the basics. Actually, maybe not quick video, but just explaining the basics of electrical circuits. So the first thing we need to know about circuits is that we need to understand the definition of current. So current is whenever you see a capital I in an equation, that's current, and we measure current in amps, which is capital A. And it's basically just how much charge is flowing per time. So 1 amp, so the current is equal to the change in, or a flow of charge per time. And so 1 amp then is equal to a coulomb per second. That's just definition stuff, all right? So what that means is if we have a wire, we have some charges that are kind of like bouncing around, and when we apply a voltage across them, what that does is that pushes those charges and they start to move down this way. And that moving charge is what we call electricity. So that's the basics there. Voltage is capital V and capital V. I did that backwards, but the variable for voltage is V. The units for voltage is volts V. So it's kind of pretty simple. We actually already talked about voltage for a while, so you should kind of know what that means. It's electrical potential, but in terms, see, I keep doing that, potential. In terms of circuits, though, you can think of voltage more as a push, as a motor. It's what pushes the charges through the wire. So the higher the voltage, the more it's pushing the charge through the wire, and the more electricity you're going to get. And then the last factor is resistance. Resistance is capital R, and the units are ohms, which is a Greek letter omega. And resistance is basically just how much, I hate to use it in the definition, but it basically resists electricity. So it's a measurement of how much the wire or the whatever you're putting in your circuit, how much it is being resisted in the thing. Let's see if I can slide this up. How do I slide this up? Oops. Sorry. Nope. Guess I'll just use the old regular mouse. Um, so those are the three like most important things, and those three things together, they're related to each other in a way that's called Ohm's law. And Ohm's law looks like this: V equals IR, where V is voltage, I is current, and R is resistance. It can be rewritten in different ways, so we can have current is equal to voltage over resistance, or resistance is equal to voltage over current, or V equals IR. These are all the same equation, they're just rewritten three different ways. No big deal. Next up is circuits. A circuit will look like this. We have a battery, and we touch a wire to that, and maybe we have a light bulb, right? And then we touch that to that, and then maybe we have a resistor. But here's the thing. If electricians or whoever's drawing these diagrams had to sketch out a light bulb like that or a battery like that every time they were making diagrams, it would get tedious. It would get like in the way. So what we use is we call a schematic is basically just we use symbols for these things, and we look at circuits in a different way. So this is a battery, and this is the positive side of the battery, that's the negative side of the battery. And anytime you see a line, it's a wire. A resistor is a zigzag line. A light bulb can be a couple different things. Sometimes it looks like that, like a Pokeball. Sometimes it looks like an X, like that. Sometimes it looks like a loop-de-loop. Basically, if you see a circle, it's probably a light bulb. Switch will look like this. They always show switches as being open because if it was closed, it would look like that, obviously, and that would get confusing. So they show the switch as being opened. I should probably be labeling these resistor, light bulb, battery. These are the most common things that you're going to encounter in this class. In other classes, you might see some other things, or if you actually become an electrician or electrical engineer, you're going to need to know thousands of them, or at least hundreds of them, and then be familiar with thousands of them. But anyway, this is the basics. Now let's talk about the basics of circuits, because there's a couple rules to circuits. So circuits, in order for electricity to flow, they have to be closed. So if you have a battery and you have a light bulb, I'll just make it an X, and you just kind of have that, this would not be closed. There would be no circuit. There's no electricity. Even though we are connected to two ends of a battery, if we don't connect these two ends here, then it's not going to light up. So if I connect these two like that, then we're going to get electricity, and therefore we're going to get the bulb to light up. So it has to be closed. Another thing that happens sometimes is called a short circuit. And a short circuit is when you basically just say, hey, let's just directly connect the two ends of the battery with no resistors, no light bulbs in it at all. So let me show you an example of a short circuit. If I took a wire and connected it from here to here, this would make the light bulb go out, because if I connect it from here to here, the electricity is going to go like this. And then once it gets up to this point, it has a choice. It can either go through the light bulb or not. And guess what? It's going to be like, yes, screw that. I'm not going through the light bulb. I'm going to just go right back to the end of the battery, and I don't even have to go through the light bulb. Because remember, light bulbs are resistors. They're just fancy resistors. They also give off light. So there's resistance in a light bulb, so the electricity is going to be like, let's just stay in the wire. So that's a short circuit. If you've heard about people's phone chargers heating up and, burning people or things like that, that usually means that there's a short circuit, because when you get a short circuit, you usually get some sort of flame or heat, because the electricity is going so fast that the wire gets so hot, and then it can cause a burn or something like that. So that's why short circuits are not really good things. We tend to not want them to be in our circuit, because they bypass all the stuff that we design for, like light bulbs, and they get hot and they could melt things. So that seems like the basics of all, just like the kind of, we talked about earlier, how batteries, this is the positive end, this is the negative end. Most batteries are 1.5 volts. There's a 9-volt battery. A car battery is 12 volts. Not really super important stuff for you to know, but good enough. And then there's also resistivity. Resistivity is a measurement, so it's related to resistance. Its variable is rho, which is a Greek letter, and its units are ohm meters, so it's an ohm times a meter. And resistivity is a measurement of, the material. So like, for example, copper or aluminum or silver, like depending on which thing it is, it has a different measurement of resistivity. And resistivity is basically just how resistive is the material. It gives you an idea of how much that material resists electricity going through it. Now, these three things are great conductors, which is something else we talked about. Great conductors mean that they do actually transport electricity very well, so they're really good at that. But something that is a bad conductor, like plastic, that would have a very high resistivity. So just to give you an idea of what that means. There is one equation for resistivity, and it looks like this. This is resistance, not resistivity, is equal to resistivity times the length of the wire divided by the cross-sectional area of a wire. So if we have a wire, and this right here is the cross-sectional area, and then this right here is the length, right, from here to here, and then the resistivity is a property of the material. That would be a number that would either be given to you or you have to calculate it. And then we have R, which is the resistance, and that's measured in ohms. And basically, if we look at the dimensions of a wire, the dimensions mean a lot in terms of, dimensions are important to the resistivity of the wire. So basically, if you have a short and fat wire, that's going to be a very low resistance, right? Because take a look at this. If I make this very small and I make this very big, then that's going to make this number really small, right? But then if I have a very thin wire, right, the cross-sectional area is really thin and I have a very long wire, what happens is if I make this small and this large, then that makes the resistance big, right? Whereas the other way around was if I make the length small and then I make the area big, then that makes the resistance small, right? So basically, long wires have high resistance, tiny thin wires have high resistance, short fat wires have low resistance, so they're really good conductors, which means for you that if you're plugging something into the outlet or you use an extension cord, we talked about this a little bit more, but if you plug in something to an extension cord, you're making it longer, so you're increasing the length, which means you're going to increase the resistance. And again, that could get hot and then melt. So that's why some things you're not supposed to plug into extension cords, like portable heaters, hair dryers, and vacuums, things that have high power outputs. Let's talk about power real quick. Power is equal to current times voltage. So this is electrical power. And power is still measured in watts, right? And the capital P is the thing for it. So power is equal to current times voltage. So if the current is 3 amps and the voltage is 120, then the power output is going to be 360 watts. And you can go back and forth with that equation. You can also use Ohm's law to substitute in for any of these things. So if I want power to be in terms of current and resistance, then it would actually be I squared R, because if I plug in basically, so IP equals IV, if I substitute V for IR, then I have P is equal to I times IR, right? Substituting that V for IR, then that equals P equals I squared R. And that's another equation for power. And another one would be in terms of voltage and resistance, and doesn't include electricity or current at all. So these three equations are for power, but they're really just the same equation, just using Ohm's law to substitute into those. But yeah, so if a question says something about watts, right? Or if they say something about power or energy, don't forget that this is from your energy unit. Power is the rate of change of energy over time, or work per time. So let's say that we have a 100-watt light bulb. That means that that light bulb is giving off 100 joules of energy per second, right? Because that's joules and that's seconds. So that's what watts means. So if we say that a toaster has 600 watts, that means that it's spending 600 joules of heating energy every second to your toast. That's what that means. All right, I'm trying to think. I'm pretty sure that's all the basics of circuits without getting into the nitty-gritty circuit analysis stuff. Wow, I cannot draw a straight line to save my life. There we go. So the last thing I want to talk about is circuit analysis. Circuit analysis is when you look at a schematic, right? So let's say it looks like this. And when you look at a schematic and you're given certain values, like let's say that this is 12 volts, whoa. And this is, you know, we know the values of these. Let's say that's 10 ohms, and that's 10 ohms, and that's 5 ohms. Circuit analysis is when you look for either voltages, resistances, or currents based on some kind of circuit that you have. And circuit analysis can either be easy or it can be kind of complicated. So I want to just go over the very basics real quick, and then we'll get into the harder stuff. So first thing you need to understand is what the difference is between series and parallel. A series circuit is when you have things like resistors. I'm just going to talk about resistors. And the resistors are basically in order. So we have resistor 1, resistor 2, and resistor 3. And if you follow the electricity, there's only one path for it to take. It has to go through all three of those resistors. That's a series circuit. A parallel circuit is when you have a choice, or when the current can split. So let's say that we have a resistor here like that, a resistor here like that, and then a resistor here like that. So if we look at this scenario, there's three different paths that the electricity can take. It can go like this. It can go like, whoops. It can go like this. Or it can go like, I think you know what's coming next. This. Now, a parallel circuit only needs like one junction, and a junction is a place where current can split. So at that point right there, current splits into three different currents. If you're splitting current, that's a junction. Notice that there's no place in a series circuit where there's a junction. There's no place where it's going to split into any other currents. So there shouldn't be any junctions in a series circuit. That's the main difference between the two. There's a couple other tips that I can write for you here. Number one, things for you to memorize. Current in a series circuit, so I'm going to draw it like underneath here. In a series circuit, the current is the same at every point. Because if the current can't split, then that means it has to stay constant. So if the current here is 3 amps, then that means the current here is 3 amps, and here is 3 amps, and here is 3 amps, and here is 3 amps. It's 3 amps everywhere. So that's number one. Current is the same at every point. Number two, finding the equivalent resistance is easy for a series. All you have to do is just add them up. It's R1 plus R2 plus R3 plus however many resistors you have, just add them up. So if this R1 is 1 ohm and this is 10 ohms and this is 3 ohms, you would just do 1 plus 10 plus 3, and the total resistance of that circuit would be 14 ohms. All right, so it's pretty straightforward, pretty easy for finding series circuits. The only thing about a series that is a little bit complicated is the voltage is not the same everywhere. But we do know voltage. I'm just going to put C. Kirchhoff's rules, and we're going to talk about those in a second. I spelled that wrong. Two H's. All right, now let's come over here to parallel. In the parallel, the current is not the same. The current splits at junctions. And to figure out what the current is, we're going to reference Kirchhoff's rules, which I'll talk about again later. Whoops, rules. To find the equivalent resistance, it's 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And to show you a quick example of how we can solve that, let's just give these some numbers. So let's say that this is 4 and this is 12 and this is 8. So I would say 1 over Req is equal to 1 over 4 plus 1 over 12 plus 1 over 8. Now, I talked about this in my other video, but I want to make it clear. A lot of my students have trouble with math. This math, in my opinion, I think is like at a minimum of 6th grade math. So yeah, I'm shaming you a little bit. If you're struggling with this, you either, yeah, I'm not shaming you for not knowing it. I'm shaming you for not getting the help that you need to understand it, because this is something that you should already know years ago. And so anyway, I'm done shaming you. You should be able to do it after I show it to you at the very least. First of all, you cannot just flip everything immediately and be like, oh, well, they're all 1 over, so I'll just say REQ is equal to 4 plus 12 plus 8, right? I can just flip them all, get rid of the ones. Doesn't work that way. You can't cancel out all the ones and just be like that. That's not allowed. That's illegal. So you can't do that. Whoops. What you do is, when you see this, usually these numbers are pretty nice in the sense that they, like I have 4, 12, and 8, so they're all pretty closely related to one another. So my opinion is, or my suggestion is, for you to just find common denominators. So 12 is the biggest one here. So 8, 12, and 4, I would say probably the best one would be 24, right? So what we're going to do is we're going to make these all 24 denominators. Now, hopefully you remember you cannot add fractions unless they have the same denominator, right? So how do I get 1/4 to 24? Well, 1/4, you would just multiply. How do I get to 24 from 4? I have to multiply 4 by 6, right? So that would be 6 24ths. 24, or 12 times 2 is 24, and then 8 times 3 is 24. So I have 6 plus 2 plus 3. Now I can add them all across. So 6 plus 2 plus 3 is 11. 11 24ths is not a nice number, but that's what we have because I made this up on the spot. Now here's the second place where kids mess up. And they basically look at this and they say, oh, that's my answer, I'm done. This is not the equivalent resistance. This is 1 over the equivalent resistance. We want to get REQ by itself. So the way that we do that is we can just take the reciprocal of both of these. Now we can, because we're not doing any more addition. So it's REQ is equal to 24 over 11 ohms. You can simplify that in your calculator. Like I said, it would be nice if it was nice, but it just didn't turn out that way because I made it up. So that's how you find the equivalent resistance, which is admittedly a little bit more complicated. But the last thing that's a little bit easy, that kind of, I guess, redeems everything here, is that voltage is the same across each branch. So what I mean by that is, let's say that this is connected to a battery, like that. Let's say this battery is 24 volts. That means that across each one of these is 24 volts. And you can memorize that. That's something that's true for every parallel branch. The voltage is the same across each one. All right. So those are some tips for series and parallel. Let's finally just move on and start talking about, oh my God. Let's start talking about how to do circuit analysis and Kirchhoff's. Let's talk about Kirchhoff's. There's 2 rules. Pretty straightforward. Rule number 1, we'll call it the loop rule. The loop rule says that any loop, any closed path loop, in any closed path loop, the voltages must add to 0. So we say, let me draw one for you. So here's a battery. I have resistor, resistor, close, and then let's say I have resistor, close. Okay. So this is a complex circuit, right? The current can either take this path or it can take this path. So any loop that we pick, there's 2 loops here. There's the pink loop and the green loop. Either one that you pick the voltage has to add up to 0. The battery voltage is positive, and the voltage drops across the resistors are negative. So let's say that this is 12 volts. What's the voltage drop across this resistor? Well, 0 is the total. It has to add up to 0. So then it'd be plus 12 going across the battery, and then minus the voltage of the resistor. In this case, that would mean that this would have to be 12 volts, right? Minus 12 volts. If we do the green one, let's say that we know that the voltage across this one is 3 volts. What's the voltage across this one? Well, the sum has to be 0. Positive 12 across the battery, negative 3 across that one. So then what is the voltage across that last resistor? Well, 0 is equal to 12 minus 3 minus x. What is x? X is going to be 8, right? Where x is basically just the voltage VR, I should call it, I guess. So 8 volts. All right, so that's what the loop rule says. So any closed path that you pick has to add up to 0. Let's do an easier example just so you can make sure you totally understand it. If I have a series circuit, and let's say I have voltmeters across those two. Let's say the battery is 12 volts. This is 4 volts. This is 3 volts. What's this one? Then you would just say, well, it has to add up to 0. So I have positive 12, and then minus 4, minus 3, minus that last voltage. What is that last voltage? 8 minus 3, so it's got to be 5, right? So that's the loop rule. The second one, hello, there we go, is called the junction rule. I think this one's a little bit easier. The junction rule just says that at any junction, the current in must equal the current out. So that's a fancy way of just saying, take a look at this. Let's say here's my junction. Let's say that this is 10 amps coming in from this point, and then when it gets here, it can split into 2 different currents. And let's actually have it do this. Okay, so let's say that we know we have an ammeter here. Let's say that we know that that current is 3 amps. So then what is that current? Well, if we look at it, we have 10 amps coming in, and we have 3 amps leaving. So the current in has to equal the current out. So what is that current? That's current has to be 7. That's a junction rule. And then when it comes back, if we have 7 and 3, then this has to be 10, right? When it comes back together. So that's kind of the main idea of the junction rule. I don't really know how to elaborate on that. Something else that just came to mind too that I should have said earlier, I probably should have put it up in the other thing, is ammeters and voltmeters. You have to put them in the circuits in particular ways. So let's say that I have a circuit here. I'll just do one resistor. Okay, if I want to measure the current in that, I have to put the current or the ammeter in my circuit, meaning I have to kind of let me just do this real quick. So I have to put it in there and force the current to go through that ammeter. That's in series. So ammeters have to be in series. And then if I want to know the voltage drop across this resistor, I have to find the voltage drop by doing it in parallel. So that's the main thing that you need to know about voltmeters and ammeters. I'm going to take a break, and then I'm going to explain some complex circuits in a second.